Express this in partial fractions. So let's just check the order. The denominator has an order of 3, the numerator of 2. So we're all good. We don't need to do polynomial division. We're going to get a over x plus 1. And this is one of those ones where you can't factorize it using real numbers. So we go with bx plus c as our numerator, and all over x squared plus 4. Let's multiply through by the denominator. So then we will get 2x squared plus 3x plus 6 is identical to a times x squared plus 4 plus bx plus c times x plus 1. Amazing. Now I'm going to do a combination of comparing coefficients and subbing in for x. I mean, it's up to you exactly how you do it. But I think subbing in for x is a good shout to start with. X equals minus 1. We'll just get rid of that whole right-hand term, which is ideal, really. So we'll get 2 minus 3 plus 6 equal to, well, minus 1 squared is 1, plus 4, that's 5. 5a. Check out the left-hand side actually becomes 5, so a is going to equal 1. 1 down. Now, good shout is to go with x equals 0, because that will get rid of b. So I will get, it's just very easy to sub in 0. So we get 6 equals 4a, which is just 4, because I've worked out what a is. And then it'll be plus, well, it's just going to be c times 1, so c. So c is equal to 2. And then finally, I'll use the coefficient of x squared. Because this is an identity, this is true for all values of x, we can compare coefficients. So it must be that 2 is equal to a, because we've got 2x squared equals ax squared, so that's just 1, plus b. So b is equal to 1. And therefore, this becomes 1 over x plus 1 plus x plus 2 over x squared plus 4. And we've written it in partial fractions. And show that the integral of that function between 0 and 2 is equal to a ln of something plus a multiple of pi. Okay, so let's just call this I, and then I is going to equal the integral of 1 over x plus 1. I'm going to separate into 3 integrals actually now. Okay, because I know, like basically, if you know how to integrate it, then just go for it. Just separate it basically. Now this one here cannot just be integrated directly. When you differentiate the bottom, you get 2x. It's not like it's in the form f dash x over f of x. So what I'm going to do is separate this one as well. It's going to be the integral of 0 to 2 of x over x squared plus 4. And then we're left with this one here. And this latter one is actually quite a standard integral. It's in the formula book. So a little bit of work to do. If I look at so this one is nice. I'll deal with that in a minute. It's going to be ln. This next one is not quite in the right form because when I differentiate the bottom, I get 2x, not x. So I'm going to times through by the top by 2 and then times by a half. So that doesn't change it, but now it's in the right form. And then this other one, I'm going to bring the 2 out and write it as a 1 here. Because the formula book says that when we integrate this, then we get this. So that 4 is actually 2 squared, and so I can just swap them around. Let's deal with it then. So I'm going to get ln of x plus 1. And remember, we know that when we differentiate ln x, we get 1 over x. When you differentiate, say, ln x plus 1, you're going to get 1 over x plus 1 and times by the derivative of the inside. That's just 1. So it all works out. And then the next one, this is in the form f dash x over f of x. It will be a half ln x squared plus 4. Sorted. And the last one is going to be 2 times, right, now it's 1 over 2 tan to the minus 1 of x over 2. And I'm going to bring it back inside, like, I mean, rather than having 3 separate limits, I'm just going to bring it back together now and put a 2 here and a 0 here. Okay, let's sub in. Put in the upper limit, we've got ln 3. Then it will be plus a half ln 2 squared plus 4, that's 8. So half ln 8. And then, of course, these cancel. So I've got plus inverse tan of 1. And then I'll be minusing ln 1 plus a half ln 4 plus inverse tan of 0. Well, ln 1 is 0, inverse tan of 0 is 0. So I've got ln 3 plus a half ln 8 plus inverse tan of 1 is actually pi over 4. And then I will be minusing a half ln 4, which I'm going to leave. I could write it as ln 2, but I'm going to leave it as a half ln 4 for the moment because that will make it easier to combine these two. So I'll get ln 3 plus a half ln 8 minus ln 4. That's actually just 8 over 4, or 2. Okay, and we are very close. Just bear in mind, we're asked to leave our answer as ln a root 2. So that is precisely what will happen here. That half, I can just raise 2 to the power of a half and then write it as root 2. I'm going to get ln 3 root 2 plus a quarter pi. That is our answer to this integral. Lovely.